Good morning, guys. Hope you guys are enjoying your day off. Hope it is fun, productive, or at the very least not boring, unlike what this should be today. So let's take a look at some of the review problems we have to prep us for our final here coming up in a couple of days. Let's start for today with a couple of reminders to remind us of how we're supposed to fit all these pieces together. Reminder number one, a trig function represents a relationship between sides of a triangle. This could mean that they have individual sides that directly relate or indirectly relate to our particular problem. And again, this is for a triangle, meaning it could mean that we have them for all triangles, the same, or triangles that fundamentally look different but have the same properties. This is referred to in geometry as similarity versus congruency. Again, it just represents a relationship between the sides of a triangle. Our job is to connect it to the sides of the triangle we want to produce. It is not a requirement they be the same. They are related. It is a relationship. Two, if one trig relationship is true, then all six trig relationships are true. This would be helpful for what I refer to today as the indirect problems. These are problems where they don't quite fit the relationship the way they are expressed, so we'll have to use some other trig relationship and some fancy math to determine that missing component we need to actually solve these problems. Let's take a look at today's problems, and they look something like this. Given one side of a triangle and a trig relation, find all other sides of that triangle. Now, we've seen examples of this already using some of the problems from about 3 weeks ago. These include given a single side, so we have here side C of a triangle is known, and a single trig relationship, sine of theta, is equal to 4 over 5. Now, the important distinction here is that we have a single side that is known, and that is known as a trig relationship for either sine, cosine, tangent, or one of the other three. Now, in this particular style of problem, it is assumed that this side C equals 12 is the standard sides of a triangle, where we have C opposite the hypotenuse, A opposite from angle A, B opposite from angle B. So to start these problems, the first step I recommend every single time when we have our given information is step one, let's draw two pictures. The first picture is going to be to take the information given from the sides. So in this case, we need to take side C is equal to 12 and put it into a picture. The second piece will come from the trig function, the trig relation. Sine of theta is equal to 4 over 5. Now, this will split our problem into two separate categories. Once we've taken our pictures, it will split into two categories. Option A is going to be the direct method, which this problem actually is great for the direct method. We'll do one more example with the direct method so we can see fully how these fit together. Option B takes this exact same problem, and instead of being the direct method, we'll refer to it as the indirect method. The difference being the trig function versus the side, how well do they fit together? If they fit together directly, it's the direct method. If they don't quite fit together, it's the indirect method. Involves an extra step or two, but it's the same basic principle. So step one, we're going to set up our two pictures. Here we go. I tend to draw a standard picture most every time. There's my angle theta, which if you remember from our standard algebra and from our setting up, this would make this angle A, angle B, angle C. This would make, according to my picture, this side little a, this side little b, and this side little c. Now, taking the information we given from the problem, again, the information c is equal to 12. So I'm going to take this side, c, and make it equal 12. Now, we take a second picture. The second picture comes from the trig function. Sine of theta is equal to 4 over 5. Now I'm going to draw a similar looking picture. It's going to be a different size, but it's going to have similar properties. That's the goal here. Similarity from geometry. So again, it's going to look similar. It's going to also have angle A, angle B, and angle C. It's going to have theta in the same spot as the previous picture. So these two are similar, but not congruent. So they're not exactly the same similarity. Now what's the trig function say? It says that sine of theta is equal to 4 over 5. What does that mean? It means that the opposite to theta divided by the hypotenuse to theta is equal to 4 over 5. Meaning in my picture for the second version, the hypotenuse is a 5 in value, And the opposite, so that would be in this case, this side over here, is 4. Notice for this particular triangle, these two are not exactly the same. The left-hand triangle contains values of 12 for the hypotenuse. The right-hand triangle contains a value of 5. They don't match. That's a problem. Because if they match directly, well, then we would know all the sides automatically. Or we could use the Pythagorean theorem to find either they're missing. Because these two don't match perfectly, I need to find some way to figure out, well, what's A and what's B. Now, here's the important piece. Remember, these two are referred to as similar. That means they will share certain properties, including the trig functions. Meaning, for this picture here on the left-hand side, the trig functions on that left-hand side will match the trig functions on the right-hand side. Because remember, the trig functions represent a relationship between the sides of a triangle. Meaning if they match for one of these triangles, it will match for both of these triangles. Now let's take a look. In this first picture, we can see from the first picture that sine of theta is equal to the opposite of theta, which would be A, divided by the hypotenuse of theta, which would be 12. Don't confuse little a with the adjacent. Yeah. It isn't always the adjacent. Little a is just opposite of A. Whereas in this picture over here, we know that sine of theta is equal to 4 over 5. Now it is important to note that I could obviously do other trig functions. Like I could do cosine, I could do tangent. And here's the thing. This missing side up here, so in this picture, cosine would be b over 12. Tangent would be a over b. Beautiful. And in the picture over here on the right-hand side, cosine of theta. I have to know this missing side to do it, but it could be done. And tangent of theta, I'd have to know this missing side. So for right now, I'm going to call it, let's just call it something random, k. And so cosine of theta would be like k over 5. And tangent of theta would be like 4 over k. What's important to note here is one of these trig functions is especially useful because of how they're designed, the signs. Notice that sine of theta here on the left-hand side is equal to a fraction with a single variable, one variable. That one variable is really important because when it comes to trig functions, and any function in general, you have to have a single variable to solve the problem with one equation. On the other side, we have sine of theta is equal to 4 over 5. These other 4 trig functions are useful, but not really. You see, they don't relate together one side with one variable. The other one's the cosine that we just had. That cosine function had 2 variables. It had b and it had k. And the tangent had 4 variables. That's clearly the worst possible thing I could do. So in this case, sine, you'll notice, has this unique relationship. I have 1 variable and 3 number values. And that's really important. So what I'm going to do now, with step C, is I'm going to perform a substitution. What that means is, everywhere I see a sine of theta, I can replace with a over 12, including to the second equation. And again, anywhere I see a sine of theta, I can replace with a over 12. So over here, sine of theta equals 4 over 5 becomes the equation a over 12. A over 12 equals 4 over 5. Algebraically, this is perfect because in this example, I now have one equation, one variable, solvable. So I take this missing side, which now contains the single variable a, and I solve for it by using cross multiplication. So I take a times 5, getting 5a. I take 12 times 4, give me 48. And then divide both sides by 5, trying to get a by itself. I end up with a equals 48 over 5, or 9.6. What I've done is I've used a single trig relationship. A trig relationship, which remember, represents sides of any particular triangle that matches properties. And I've used that relationship to solve for an unknown value, which we've called A. Now that I know what A is, going back to the original picture, I now know that A has to be equal to 9.6. And if I verify this, I can easily check that I've done everything correctly because I can take sine of theta. So now that A is 9.6. 4 over 5, you'll remember, is equal to 0.8. 9.6 over 12 is also equal to 0.8. So the sine relationship is still true for both of these pictures, meaning I do in fact have a legitimate problem. Now, once you have two of the sides in this picture, I have the 12 given to me from the original problem. I have the 9.6 from now my sine function being solved. I can find side B using Pythagorean's theorem, which is the last step. Step 4, I use Pythagorean's theorem to find the final missing side using what I now know. I know from Pythagorean's theorem, remember Pythagorean's theorem, a squared plus b squared equals c squared. And from my picture, I know that my a is 9.6. 9.6 squared. My b is unknown. My c is 12 squared. Doing some fancy arithmetic here, I can find that missing side. It ends up being that b is equal to 7.2. Again, I use Pythagorean's theorem with my two now known sides to find the actual missing side. You'll note that the right-hand triangle, this one up here, we only used to set up this specific trig relationship. However, that was because we could use it directly. We could also use that same triangle by an indirect method, which I will showcase here after this next example. So let's take this moment. We're going to reset and follow the exact same 4 steps to doing a new problem with new pieces that are known using the direct method. Let's take a look. Okay, let's take a look now at our new example. So the same basic concept is going to be applied here. That we're going to have some known side, some known trig function. We're going to follow through on these 4 basic steps and use that to find out the missing sides of these triangles per the instructions. So to start with, step 1 again, draw 2 pictures. Now I'm going to set my pictures just like I did before. One picture to have A, B, C. Another picture that I want to look similar but not the exact same. There we go. So I have again A, B, and C. Notice for my problem, it tells us that side B is 9. So remember, B is opposite of B, so that means this side is a 9. That also means that this side is little c, this side is little a. Okay, now according to our trig function up here, tangent of b is equal to 2. Now you might notice that this case, I have tangent equal to one number, not a fraction. We're going to have to fix that. So my first step, I need to fix this tangent. I do so by using a property of algebra, which states that anytime I have a single constant, like 2, I can turn it into a fraction by putting it over the number 1. So I take 2 and turn it into 2 over 1. This is useful because remember, tangent is defined as being opposite over adjacent. So now I can go to my second picture, which I have somehow managed to mess up. Oh, lordy, no. Okay, let's do it right. Must match. So there's B, there's C. All right, that's better. Whew. I was scared. Levi, why didn't you tell me I did it wrong? What's wrong with you, man? Garrett, I couldn't imagine you doing this wrong. Okay, I take my opposite of B to be 2, my adjacent to B to be 1. Now, from this point, I'm going to follow through the same basic steps I did before. I'm going to begin by taking my function, my trig relationship, and trying to compare them either directly or indirectly using the trig ratios. The best one to start with is always the one you are given. So if I'm given tangent, I should try to start with tangent. If I was given sine, like on the previous problem, then I should start with sine and see if it works first. Again, use the one you were given to try to solve this. Let's do it. So in this case, for my trig ratio, here we go. Let's start with tangent. Tangent of b from this left-hand picture would be the opposite of b, 9, over the adjacent to b, which is a. From the second picture, tangent of b is equal to 2 over 1. This is great. You'll notice that I have a single variable, a, and 3 numbers. This is the golden place. This is the golden zone. I have one variable with 3 numbers. Perfect. I move to step 3. I'm going to apply a direct relationship to try to solve this. According to step 3, I want to do a substitution. That means anywhere I see tangent of b, I can replace it with 9 over a. So I go over to my second equation over here. Tangent of b is equal to 2 over 1. I replace tangent of b with 9 over a equals 2 over 1. Again, simple substitution from algebra. I take a known tangent of b and plug it in for the other tangent of b. Tangent of b is equal to 9 over a, so anywhere I see a tangent of b, I change it to 9 over a. You could obviously do the opposite, where I take the tangent of b from the first equation and have it plugged in from the second. It gets the same results. Pick your poison. From here, I can now use an algebraic property to solve. I take 9 times 1, doing cross multiplication, which is 9. I take a times 2, which is 2a. And now I'm solving. Divide both sides by 2 to get a by itself. I end up with a is equal to 4.5. Which means, according to my picture, this side again is 9. This side is now 4.5. I have two sides that are known. Step 4 says we do Pythagorean's theorem. So I do Pythagorean's theorem. I have two known sides. Let's set it up and solve. According to Pythagorean's theorem, a squared plus b squared equals c squared. Remember, my a and my b are just my two legs, so I have 9 squared plus 4.5 squared equals the unknown c squared. And from here, what I can do is I can solve it manually to try to figure this out. So I will do it now on the board, unlike the last one where I just did it with the calculator. 9 squared is 81. 4.5 squared, let's see, that would be 20.25 equals c squared. I add those two together, I get 101.25 equals c squared. I then take a square root of both sides to get c by itself. It turns out my missing side c is equal to the square root of 101.25. And that's my solution. C is equal to 101.25 inside the value. Notice in both of these cases, I've used a given trig relationship to find the missing components of one side, then use Pythagorean's theorem to find the other, a mixture of different trig topics to come to a single solution, which is the missing sides of this triangle. Notice I used to use properties of algebra, like substitution, in order to make this work well. Now, these two examples are basically the direct method. This method is the preferred method. It's the easier method. Our next two examples are going to be the indirect method. What happens if this first step here fails? Where I end up with, instead of a single variable, I end up with more than one variable. What are my options? How do I solve this then? Well, let's take a look. Okay. Notice that this time I'm given c, just like the first problem. This time I'm given tangent, just like the second problem. But the side and the trig function are not important. It's the relationship between them that matters the most. It's how it fits in with the components we're looking for that matters the most. So let's take a look at this problem now, following these same 4 steps, but this time you're going to notice that the direct method is going to fail. And we'll see exactly how that happens here in just a second. Let's go. Step 1, I start by drawing my picture. Again, it does not matter how you draw this triangle. It doesn't have to be accurate as long as A, B, and C, and the other one matches to it. Again, similar, not exactly the same. A, B, C. Don't forget my little right angle symbols. There we go. Now, according to the given of the problem, it states that C is equal to 8. So I go to my picture, C is 8. In my second picture, it says that tangent of A is 3 over 2. So here's my angle A. The opposite, remember tangent is opposite over adjacent. So the opposite of A, that'd be over here, has to be a 3. The adjacent to A, which is down here, would have to be a 2. Now, once I've got my two pictures, I now go into step 2 to try to take these into two categories by setting up a trig ratio. Let's begin, exactly like we did the previous ones, with the one I'm given in the problem, tangent. Here we go. According to this picture, tangent of A is equal to 3 over 2. Beautiful, fantastic, wonderful, amazing. Okay, but if I go over to this picture, tangent of A, okay, well, opposite to A is little a. It's unknown, so I have to leave it as little a. Opposite or adjacent to A is this side over here, which we know as little b. Uh-oh. I get to this point, you notice that I have two variables, an a and a b. This is a clear problem. I'm not supposed to have two variables if I want to solve this problem. If I try to set up my two fractions and do a simple substitution, I will end up with a over b equals 3 over 2, which is unsolvable. Again, a over b equals 3 over 2, doing the substitution like we did in the previous ones. I then cross multiply, I get 2a equals 3b, and then how do I solve that? I divide by 2, well then I get a by itself, and then what's b? I divide by 3, or I get b by itself, but what's a? So this is unsolvable. So at this point, I know the direct method will not work for this specific problem. That does not mean the direct method doesn't work. It's because of the two pieces I was given, the C and tangent. You will find that for some problems, C is great. Other times, C is terrible. It depends on the trig function. Sometimes tangent is great. Sometimes tangent is terrible. It depends on the problem. You have to be able to find those components. So if tangent fails, then I have to go to some other trig function, which means I now am left with either sine or cosine. Now, remember, in one of my pictures, I do sine. In my other picture, I do sine. In one of my pictures, I do cosine. In the other picture, I do cosine. They need to match. So let's look at this problem again using sine or cosine. Well, if I look at this picture, sine of A, remember, is opposite of A divided by the hypotenuse. Well, the opposite of A, so here's little a, opposite of A would be A over the hypotenuse, which is 8. Well, that's good. I have a single variable and a number. That's a good start. The problem is, if I try to do sine of A on this side over here, the opposite is 3. The hypotenuse is unknown. However, unlike with the previous problem, this particular unknown is good. It's easy to find because you'll notice that in this triangle, I know 1, 2 sides. I can find the missing side using Pythagorean's theorem. So if you're going to do the indirect method, odds are you'll have to do Pythagorean's theorem early to find the missing side of this triangle over here. So let's do it. I set up my Pythagorean theorem. 2 squared plus 3 squared equals c squared, the unknown. 2 squared is 4, 3 squared is 9, c squared is c squared. I don't need this because this, remember, didn't work. Okay, let's solve. 4 plus 9 is 13 equals c squared. I can now know that c is equal to the square root of 13. Meaning on this side, c is the square root of 13. This c can be found. And it's important to note, I could have found it on the previous two problems as well. I didn't need to, though. I could find directly the answers without needing to do this step. This step is only necessary because the initial trig function tangent did not work. Because tangent did not work, I am forced to do this step. So I did. Let's go ahead and take the next step. Now, I know that the sine for this problem is equal to the opposite over the hypotenuse. Well, that means it would be equal to 3 over square root of 13. That was terrible. That was what you did. Square root of 13. Now you'll notice that my sine function contains one variable and 3 numbers. One of the numbers isn't a nice number, but that's okay. They don't always need nice numbers for these problems. So now I could do a sine version of this problem, following the step 3, doing a substitution, and then step 4, finding Pythagorean's theorem afterwards. Now, you might be asking yourself, but could I do cosine? I mean, Douglas, you just chose to do sine. Couldn't I do cosine? Yes, you could do cosine. It was set up slightly differently, but it would still work. Here we go. The cosine one would, instead of being cosine, it would be, let's see, be b over 8. And then on this picture, it'd be 2 over square root of 13. And we could solve that one. But you notice that sine will solve for a, cosine will solve for b. So I could do either one. If I really wanted to, I could do both and find a and b directly and avoid step 4's Pythagorean theorem. However, most people think Pythagorean's theorem is easier. So I'll continue using these same 4 steps every time. So I can choose which of these 2 trig functions I now want to use. I choose to use the sine function. Okay, let's do it. Now I do a substitution. Anywhere there is a sine of a, I'm going to replace it with a over 8. With the sine of a over here, which means that instead of writing sine of a equals 3 over the square root of 13, I'm going to switch out sine of a for a over 8 equals 3 over the square root of 13. I do the same as before. Cross multiply. A times the square root of 13 is a square root of 13. 8 times 3 is 24. I divide to get a by itself. A is equal to 24 over the square root of 13. Using a standard arithmetic rule, I know this would be 24 square root of 13 over 13. If I really wanted to, I could grab out a calculator, and if I do, I would end up with a solution of something close to 6.6? 6.6? Sure. 6.65? Yeah, sure, why not? Okay. Now, I know on its inside, A is either the 24 square root of 13 or 6.65. Calculator says 6.56. There we go. From here, I now do the last step as before with Pythagorean's theorem to find the missing side b. So I'll do that last step. I use 8 and the 6.656. Let's set up one final Pythagorean theorem, step 4. The final Pythagorean theorem says 6.656 squared plus b squared equals 8 squared. And then I solve. I'm not going to lie to you. Calculator is your friend. 8 squared is, of course, 64. That number squared is 44.307 plus b squared. Add and subtract. I get b squared is 19.69 and 2. I then square root both sides, so b would equal the square root of that nasty number, but I'm going to go ahead and convert it to a decimal. You You're not free to go yet. Sorry. Did you enjoy my joke? I enjoyed my joke. 19.692. And I got the B is 4.3, sorry, 4.438. So again, this is the indirect method. We use the knowns and the unknowns to determine the missing information in this kind of problem. Note the big difference between the direct versus the indirect methods. Unlike with previous problems, where we've had a direct relationship that solves them, I am forced to use an alternative relationship. In this case, I have used Pythagorean's theorem, right here, to find the missing side, then use a different trig function. This is the indirect part of it, to determine the new trig relationship I want to use, which in this case I chose to use the sine function. I could have chosen to use the cosine function. I would have just solved for a different side first, and then eventually walked backwards to find the other side. Again, if I had done the cosine version of this instead, right here, I would have gotten the 4.43 whatever first as opposed to at the end. Again, it doesn't matter which way you go about doing it as long as you eventually get there. We'll do one more example of the indirect method, try to make it nice and clean, and then we'll see how we feel after that. Okay, last problem on the day. Let's take a look. Let's go through and see what we've learned so far. Step 1, I've got side A equals 4, cosine of A is equal to 3 over 5, two triangles. Let's do it. As with the previous ones, make sure they look similar, not exactly the same. There's A, B, C, right angle, A, B, C, right angle. I set up my sides. My side says A is 4. A means opposite of angle A, so 4 would go right here. Cosine of A would be adjacent over hypotenuse, so it would be 3 over 5. All right, now we set up the trig functions. Remember, always start with the one you were given in the problem. The one I was given in the problem was cosine of A is equal to 3 over 5. In this picture over here, let me put in my missing sides. This would be side B. This would be side C. So I try to fill in my trig functions. So in this case, for this picture, cosine of A would be equal to the adjacent to A, which is B, over the hypotenuse, which is C. I can clearly see the issue. I have two variables, no good. Now I go into plan B. I use the indirect method following Pythagorean's theorem. So I start with Pythagorean's theorem over here. I do 3 squared plus A squared, because remember A is opposite of A, so there's a little A, is equal to 5 squared. Simple arithmetic, 3 squared is 9, A squared is A squared, 5 squared is 25. Subtract 9 from both sides, A squared equals 16. Square root both sides, A equals 4. Oh, this is nice. Look at that, a nice number. This is referred to as a Pythagorean triple. Okay, so there's my missing sides. Now, from the right-hand picture, I can choose to do sine of A, which sine of A would be opposite of A, 4, over the hypotenuse, 5. Or I can do tangent of A, opposite 4 over adjacent 3. In this picture, on the left-hand side over here, I can do the same thing. So I would do sine of A. So that would be the opposite, which would be 4 over C, or tangent of A, which would be 4 over B. Notice that both of these are actually good. This one contains a single variable C. This one contains the single variable, oh, I made a mistake, silly me. The single variable B. Not C, silly goodness. So, I could use either one of these. I have to make a conscious choice which one I want to do, and then I do that one. You might be asking, well, which one? For me, in this case, I'm going to choose to do Tangent. Why not? Tangent looks pretty. I like tangent. So according to this thing, we know that tangent of A, anywhere the tangent of A, I can replace with 4 over B. So over here, where I know that tangent of A is equal to 4 over 3, anywhere I see a tangent of A, I can replace it with 4 over B. Give me this equation. Do some quick arithmetic. I find out that 4b is equal to 12, and that b equals 3. Oh, how pretty. That's the first time today we've gotten some nice numbers on all the problems. So there's 3. So this side is 4. That side is 3. I use Pythagorean's theorem one final time to find the missing side c, or I could use this other trig function to find the missing side c. Both work. Either way, you end up with a solution that c is 5. This happens to be a case where both triangles end up being the exact same, and that's actually okay. This can happen. It's just rare. Remember, a trig function represents a relationship between sides of a triangle. They could match. Most likely they will not, as has happened so far. So in conclusion today, let's review our two main things we talked about, both involving the same basic starting components. First, each of these problems you're going to be given tonight are going to be where you have one side of the triangle that is given to you and a trig relationship is given to you. You'll be asked to find all the other sides of that triangle. To do so, there are two primary techniques. You may either use the direct method when the first trig function, one that's given to you, works perfectly. It sets up to solve for one variable, we solve for it, we follow that with a substitution with Pythagorean's theorem. Option B, if that first trig function does not work, we use Pythagorean's theorem early to find the missing side of the trig ratio triangle. This one over here. You're on the right-hand side. Get one. We find the missing triangle over there, and then we use it to solve for either other trig ratio, the sine or the tangent. In this case, it's dependent on the problem. Once you have those missing components put together, we then plug them in, and we find our solution. That is it for today. You will have a total of, I believe, 6 homework problems. Relatively short for a nice snow day. You don't want to put too much on you on a nice cold Monday. But all 6 of them we have already done before. However, some of you struggled with them when we did them the first time. I want you to try them again. This time, make it your goal. Follow these 2 main steps, either the direct or indirect methods, to determine your solution. I give you 2 examples of each. Please use those to guide you on how to approach them. If you have any questions, let me know when we come into class tomorrow. I will see you guys then, and I hope you guys have a good rest of the day.